Welcome to the Curious Voyager. Tonight, let's go looking for something that isn't quite there. Something you were told existed, something you can measure, something that pushes and pulls and carries energy across a room, and yet, when you go to find the actual object, the actual little thing, there's nothing in your hand. Only a motion, only a pattern. Only a kind of coordinated hush moving through matter that behaves so much like a particle that physicists, after a while, simply gave up resisting and called it one. So settle in. Let your shoulders drop. There's no hurry here, no place we need to reach by any particular time. We're going to move slowly, the way you'd wander through a museum after closing, when the lights are low and the guards have gone home and every strange object has all the time in the world to explain itself to you. And the object we've come to see is the strangest of them all, a whole family of things that live inside solid matter, inside metals and crystals and cold liquids, and that turn out, when you look closely, to be less like objects and more like rumors. True rumors. Measurable rumors, but rumors all the same. Let me start with the thing you were taught, because we have to gently take it apart before we can put the better idea in its place. You were taught, somewhere along the way, that matter is made of particles, that if you took this table, or this cup, or your own hand, and cut it in half, and then in half again, and kept going, patiently, past anything your eyes could follow, you'd eventually reach the little building blocks. Atoms, and inside atoms, smaller things still, electrons and the dense knot of the nucleus. And the picture you were left with was a picture of stuff made of littler stuff, made of littler stuff, all the way down, like a set of nesting dolls, each one a real object you could, in principle, hold. If only your fingers were small enough. It's a good picture. It's a useful picture. And for the deepest layer, for the electron itself, it's true. The electron really does seem to be one of the genuine, fundamental building blocks. As far as anyone has ever been able to measure, it has no inside. You cannot cut it in half. It's not made of smaller pieces. It just is. But here is where the night takes its first soft turn. Because inside a solid, inside an ordinary lump of metal, the kind of thing you could pick up off a workbench, most of the particles that physicists actually track, actually name, actually write equations about and build careers around, are not those fundamental building blocks at all. They are not tiny objects hiding in the crevices between atoms. They are something much stranger and, once you make peace with it, much lovelier. They are patterns of collective motion. They are things that trillions of electrons or atoms do, all together in coordinated waves, and the doing of it, the pattern itself, behaves so exactly like a particle that the mathematics lets us treat it as one. Not loosely, not as a poetic flourish, exactly with its own mass. Its own charge, sometimes its own spin, even, and we'll come to this, its own lifespan, its own quiet mortality. We call these things quasiparticles. And the word is doing something honest if you listen to it. Quasi, as if a particle. A thing that is not a particle in the old nesting doll sense, but that wears the behavior of one so completely that the distinction stops mattering for almost everything you'd ever want to do. Now, I want to be careful with you, right here at the start, because there's a lazy way to tell this story, and I don't want to tell it that way. The lazy way says these things are illusions, fakes, tricks the universe plays. And that's not right, and it would keep you up rather than send you off, because a part of your mind would keep tugging at it, sensing the cheat. So let me say it plainly, and then let me spend the rest of the night earning it. These quasiparticles are not illusions in the sense of not existing. They carry momentum. They bounce off one another. They show up in detectors. You can use them to calculate real answers about real materials that real engineers then build real things out of. The honest word is not fake. The honest word is emergent. They are real behaviors that arise from many things acting together, real in every way that counts, just not fundamental. Not building blocks, something the whole possesses that no single part ever had. Hold on to that word, emergent, because it's the thread we're going to follow all the way through. Everything tonight hangs from it. Let me give you the purest example there is, the cleanest, gentlest, most picturable one. And it happens to be something you already know intimately, something you felt in your chest at a concert and heard in the creak of a floorboard and never once suspected of being a particle. Sound. Think about what sound actually is inside a solid. Picture the atoms of a crystal, salt, say, or the metal of a spoon, arranged in a tidy repeating grid, a lattice, like an immense three-dimensional array of beads, all held to their neighbors by tiny springs. Those springs are just the forces between atoms, the push and pull that keeps them spaced. Now, the atoms are never perfectly still. They jitter, they tremble in place, always a faint, restless hum. And if you tap one end of the crystal, if you give one atom a little shove, it doesn't just move alone. It pushes its neighbor, which pushes its neighbor, which pushes its neighbor, and a ripple of jostling travels through the whole grid, a wave of vibration passing from bead to bead down the springs. That traveling tremble is sound. That's what sound is inside a solid, a collective shiver of the lattice, atoms nudging atoms. The disturbance rolling forward while each atom mostly stays home and only sways. So far, so ordinary. But here comes the quantum turn, and it's the same turn that once, a century ago, changed how we understand light. Because that vibrational energy doesn't come in any old smooth amount. Nature, at this scale, dispenses energy in discrete packets, little indivisible portions, like coins of a currency that has no fractions. You can have one coin's worth of vibration, or two, or three, but nothing in between. Light does exactly this. Its packets are called photons, and you've heard that word. Well, the vibration of a crystal does it too. And the packet of vibrational energy, the single indivisible coin of collective trembling, has its own name. A phonon. The word was coined in the early 1930s by a physicist named Igor Tamm, and it comes from the Greek phon, meaning sound or voice. Which is just right, isn't it? The voice of the crystal, quantized, sound, chopped into its smallest possible pieces. A phonon is a quantum of sound, the way a photon is a quantum of light, a single packet of the crystal's shiver. And now I want to slow all the way down, because this is the heart of it. This is the thing I most want you to carry off into sleep with you. Ask yourself where the phonon is. If a phonon is a particle and it behaves like one, it carries energy, it carries momentum, it moves through the crystal at the speed of sound, it can scatter off other phonons and off electrons. Then where do you go to find it? Which atom is it in? And the answer, the beautiful answer, is that it isn't in any atom at all. You cannot pull a single atom out of the crystal, cup it in your hand, peer inside, and find a little piece of phonon tucked away in there. It simply isn't there. A single atom, all alone, cannot have a phonon. It can jitter, sure, but a lone atom jittering is just a lone atom jittering. It isn't a wave, it isn't a ripple, it has no phonon in it. Because a phonon is not a thing an atom contains. A phonon exists only in the relationship between atoms. It lives in the coordination, in the way the trembling of one atom is tied to the trembling of the next. It's a pattern spread across the whole lattice, and it has no home in any single piece of that lattice. Let me try that again a different way, because it's worth arriving at from more than one direction, the way you'd walk around a statue to see all its sides. Imagine a long line of people standing shoulder to shoulder, and the first one sways gently into the second, who sways into the third, and a wave of swaying passes down the line. That wave is real. You can see it move. You could time it, measure how fast it travels, watch it reflect off the far end, and come back. But if you asked, which person is the wave? The question falls apart. No single person is the wave. Each person only sways a little and settles back. The wave is the pattern of their swaying, the thing they do together. Pull one person out of the line and examine them, and there's no wave inside them to find. The wave was never in a person. It was in the relationship, in the linking, in the between. That's a phonon. And that is the whole idea of a quasiparticle, standing there in its simplest, softest form. A ripple that behaves so much like a thing that we let it be a thing, while knowing, quietly, that it lives not in the parts, but in the pattern the parts make together. And this matters, by the way. It's not just a curiosity to admire and set down. Phonons are how heat moves through a solid. When you warm one end of a metal rod and the warmth creeps toward the other end, a great deal of what's happening is phonons, packets of vibration, being created at the hot end and traveling toward the cold, carrying thermal energy as they go. The reason a spoon left in hot soup grows warm at the handle is, in large part, a traffic of phonons streaming up the metal. And when a material is a poor conductor of heat, part of the story is that its phonons don't travel well, they scatter, they get tangled, they don't carry the warmth far. So these ripples that live in no single atom are, all the same, doing the very real work of moving heat and sound through the solid world around you. The rumour does labour, the pattern pays its way. Now, having met the phonon, a quasiparticle made of the motion of atoms, I want to take you toward the harder, richer case, the one that the whole subject was really built to solve. Because the phonon is gentle. The atoms in a crystal are heavy and slow, and they mostly stay put, and it's easy enough to picture their collective sway. But there's another crowd inside a metal that is anything but gentle. And getting them to behave was one of the great puzzles of 20th century physics. The electrons. Here is the trouble. In a metal, there is a vast sea of electrons, the ones that drift freely and carry electric current when you flip a switch. Enormous numbers of them. And every single one of them is negatively charged, which means every single one of them is pushing on every other one all the time hard, because like charges repel. It's not a calm scene. It's a dense, screaming mob of particles, each one shoving all its neighbours, each shove rippling out to affect countless others, everything tangled with everything else. If you tried to write down the honest equation, every electron feeling the push of every other electron at once, you'd have a problem of such monstrous complexity that no one could ever solve it. Not with all the paper in the world, not with any computer ever built. The interactions are simply too many and too strong. By every reasonable expectation, a metal ought to be an intractable nightmare, a knot too tight to ever untie. And yet, and here is the mercy at the centre of the whole field, metals are not mysterious. They're some of the best understood materials we have. They conduct electricity in tidy, predictable ways. Their properties are so reliable, we build the entire modern world on them. So somehow that screaming mob of fiercely interacting electrons behaves, when you stand back and look at it, calmly, simply, almost as if the electrons weren't interacting much at all. As if, instead of a violent crowd, you were looking at a thin, quiet gas of particles barely bothering one another. Why? How can a dense, strongly interacting mess look and behave like a calm, dilute, weakly interacting gas? The man who answered that, who gave us the idea that lets us hold the whole thing in our minds, was a Soviet physicist named Lev Landau. Lev Davidovich Landau. And the answer he built across the 1930s, 40s and 50s and formalized most fully in his theory of the Fermi liquid around 1956 to 1958 is one of the deepest and most useful ideas in all of physics, and it's the reason we're able to talk about any of tonight's other wonders at all. Landau's move was this. He said, stop trying to track the real electrons. Don't follow the actual, bare particles with all their furious pushing and shoving. That way lies the unsolvable knot. Instead, look at the crowd as a whole and ask what the natural, low-energy motions of the crowd are. And when you do that, something remarkable falls out. The natural excitations of the whole interacting sea, the simplest ways the whole system can be nudged and stirred, behave, each one like a single particle. Like a lone electron moving through mostly empty space, feeling almost nothing. A calm, well-behaved, nearly free particle. Except it isn't a bare electron, it's a bare electron together with the way the entire surrounding crowd rearranges itself in response to it. Because when one electron moves through the sea, it doesn't move alone. It repels its neighbors, so it pushes a little clearing of thinned-out charge around itself as it goes. A small entourage of get-back that travels with it wherever it goes. The bare electron, plus that responding cloud of shoved-aside neighbors, moves together as a single unit. And that unit, the electron wrapped in the crowd's reaction to it, is what behaves like a calm, nearly free particle. Landau called this composite object a quasiparticle, a quasi-electron. And the whole trick of the Fermi liquid is that the impossible mob of strongly interacting electrons can be redescribed exactly and legitimately as a tame gas of these weakly interacting quasi-electrons. The complexity didn't vanish. It got folded up, absorbed, tucked inside each quasiparticle so that what's left to track behaves simply. There's an old, informal phrase the physics community uses for this, and I'll give it to you, but I want to label it clearly as an analogy, because if you take it too literally at 3 in the morning, it might mislead you. The phrase is that the quasiparticle is a dressed electron. A bare electron, they say, wearing a cloak, its clothing of surrounding disturbances, the cloud of shoved neighbors it drags along. So you have the naked electron underneath, and then the dressing of the crowd's response wrapped around it, and the whole dressed bundle is the quasiparticle. It's a lovely image, and it captures something true, that the quasiparticle is more than the bare particle, that it comes clothed in its interactions. But do hold it as a picture, not as a literal garment. There is no actual coat. There's only an electron and the way the sea bends around it, moving together as one. The clothing is the bending. That's all. A metaphor stitched from motion. And do you see what's happened, quietly, while we weren't looking? We've arrived back at the same idea as the phonon, dressed in different clothes of our own. Because this quasi-electron, too, is not simply a thing sitting inside the metal, waiting to be found. It's a bare electron, plus a pattern, the pattern of how the whole crowd responds. It's once again a coordination. A collective thing wearing the mask of a single particle. The phonon was a ripple of atoms with no home in any one atom. The quasi-electron is an electron plus a ripple of response with no home in any one neighbor. Both of them are the whole doing something the parts alone could not. That's the emergence idea, showing its face for the second time. And it will keep showing its face all night, in wonder after wonder, until you begin to feel it as a single truth, wearing many costumes rather than a list of separate marvels. That's the gift I most want to leave you with. Not a glossary. One idea, glimpsed again and again. Landau, by the way, was one of those figures who seemed too large for a single life. He worked across nearly every corner of physics, and much of what he touched he reshaped. His Fermi liquid theory is still, all these decades later, the bedrock on which our understanding of metals rests. The reason a graduate student today can look at a fearsomely complicated material and say, calmly, but its low-energy excitations are quasiparticles, so let me treat it as a simple gas of those, and go from there. It's a permission slip, really. Landau's great gift was a permission slip that let physicists stop drowning in the true complexity and start swimming in a manageable fiction that gives, astonishingly, the right answers. And I keep saying the right answers, and I want you to notice that, because it's the anchor that keeps this whole story from floating off into mere poetry. These quasiparticles are not just convenient ways to talk. They make predictions. They tell you how much heat a metal will hold, how it responds to a magnetic field, how its electrons will behave when you cool it toward absolute zero. And when experimenters go and measure, when they take the real material into the real laboratory and cool it and prod it and read the dials, the numbers match. The fiction pays out in fact. The quasi-electron isn't in the room the way a chair is in the room, but the predictions it makes come true in the room again and again, which is about as real as anything a physicist ever asks for. There's even a way to watch quasiparticles more or less directly, a technique with a long name we'll return to properly later, but I'll plant its name now so it feels familiar when it comes back around. Angle-resolved photoemission spectroscopy, which everyone mercifully just calls ARPS. Shine light of the right kind onto a material, knock electrons out of it, and study very carefully the ones that come flying off, their energy, the angle they leave at, and you can read, in the pattern of them, the fingerprints of the quasiparticles inside. You can see how sharply defined they are, how much they behave like clean, well-mannered particles. It's as close as we come to holding one up to the light. And what it shows, over and over, is that Landau was right. The calm gas of quasi-electrons is really in there, in the sense that matters, governing how the material behaves, leaving its trace on every electron that flies out. So let me gather up where we've come, before we drift on, because I want the shape of it to be resting easily in your mind. We started with the old picture, matter made of littler and littler objects, nesting dolls all the way down. And we found that inside a solid, that picture, while not wrong about the deepest layer, misses almost everything interesting that actually goes on. Because the things physicists track inside solids, the things that carry the heat and the sound and the current, the things that have mass and momentum and behave exactly like particles, are for the most part not objects at all. They're patterns, collective motions. The phonon, a quantized ripple of trembling atoms, living in no single atom but only in the relationship between them, coined by Igor Tamm from the Greek word for voice. The quasi-electron, a bare electron dressed as an analogy, only as an analogy, in the cloud of the crowd's response, which let Lev Landau tame the impossible mob of a metal's electrons into a calm, describable gas in his Fermi liquid theory of the 1950s, and underneath both of them, the same quiet spine, emergence, the whole hosting things the parts never contained. The pattern earning the name of a particle because it obeys, faithfully, every rule a particle obeys. Which leaves one question hanging in the dark, and I'm going to leave it hanging, deliberately, like a single soft chime you can carry with you into the next stretch of the night. If the particle isn't inside the atom, if it isn't tucked into any single electron or any single lump of the lattice, then where exactly is it? Where do you point? When the phonon travels the length of the crystal, or the quasi-electron drifts through the metal carrying its cloud, what is the address of the thing? We keep saying it lives in the relationship, in the between, in the pattern. But a pattern of what? Held where? Made real by what rule that lets a motion be counted as a particle in the first place? That question, where the particle actually is, if not in the parts, is the door we'll walk through next. Because the answer runs deeper than the phonon and the quasi-electron, deeper even than metals and crystals. It reaches into absences that carry charge, into electrons that grow 1,000 times heavier by walking through the right room, into things that are half light and half matter at once, and into a crowd of electrons that somehow hosts, between them, a thing that carries only 1/3 of a single electron's charge, even though no electron can ever be split. But those are wonders for a little further into the dark. For now, let it be enough to rest in the strange comfort of the first idea, turned over gently until it stops feeling like a paradox and starts feeling like a lullaby. The solid world around you, the cup, the table, the metal of the spoon, your own steady hand, is not the still crowd of tiny objects you were told it was. It's alive with motion, with ripples and waves and coordinated shivers, with patterns that flow and carry and behave for all the world like particles, while belonging to no single piece of the whole. The things inside matter are less like marbles and more like music, less like the beads and more like the wave that runs along the line of them. And that music is real, measurable. It moves the heat up the spoon and the sound through the wall and the current through the wire, and it does all of it without ever once being a thing you could hold. Stay with that. Let the grid of atoms hum quietly beneath your thoughts, each one swaying only a little, the ripple passing gently from one to the next, and on, carrying its small packet of energy down the line, going nowhere in particular, in no hurry at all. And keep that single chime ringing softly in the back of your mind, the question we haven't yet answered, the one that opens everything still to come. If the particle isn't in the parts, then where exactly does it live? It lives in the space between them. That is the answer, and it sounds almost too simple when it is said that plainly. But it takes a while to feel the weight of it, the way that every truly strange idea takes time to settle from the surface of the mind down into the quieter place where understanding lives. The particle isn't in any one piece of matter. It lives in the relationship between the pieces, in the gap, in the distance, in the give and take of all those atoms pressed together into something that holds a shape and a temperature and a name. And once you've let that settle, something else becomes possible. Something that the physics of solids discovered not long after the phonon was understood. Something that might be the strangest and most quietly radical idea in the whole story we're telling tonight. You can make a particle out of nothing at all, not out of energy, not out of some rare or exotic ingredient brought in from outside, out of absence, out of an empty seat, out of the blank space left behind when an electron, a real, fundamental, honest electron, gets up and leaves. Take a moment to picture a crystalline solid the way a physicist thinks about it. All those atoms arranged in their patient rows and wrapped around them, belonging to no single atom in particular, a shared cloud of electrons that flow freely through the whole. These are the conduction electrons, the ones that give a metal its ability to carry current, and they don't sit still. They drift and move and shuffle constantly, a soft, continuous migration through the grid. Now imagine, in a semiconductor, silicon perhaps, the same grey element that makes up every chip in every device you've ever touched, that the electrons aren't quite so free. They occupy what physicists call an energy band, and in the semiconductor's resting state, that band is full. Every seat is taken. Every possible energy state for an electron in that part of the structure is occupied, packed in tight, electron next to electron, with no room to move. A full room, all the chairs filled. Nobody can go anywhere, because there's nowhere to go. When there's nowhere to go, nothing conducts. A completely full band carries no current, because for current to flow, electrons need to be able to shift, to accelerate, to respond to an applied push. And you cannot accelerate a crowd in which every person is wedged tight against the next. So the semiconductor, in its restful state, sits quietly and does nothing electrical at all. But now give one electron a nudge of energy, maybe from a photon of light, maybe from thermal warmth, maybe from a carefully applied voltage. That one electron gets enough energy to jump, to leap up out of the filled band into a higher, emptier one, an energy level where it has room to move and can finally carry a current. It leaps, and it is gone, and it leaves behind a hole. The seat it vacated is now empty, just an absence, a blank. And here is where the physics gets genuinely strange, where the emergence idea shows up wearing a new face and asks you to reconsider what you thought the word particle meant. That empty seat, that pure absence of an electron, behaves, in every experimentally measurable way, like a real positive charge carrier. It behaves like a particle with its own mass, its own momentum, its own ability to respond to electric and magnetic fields. Measure it. Track its motion through the semiconductor. Do the experiment, and you will find something that moves, that accelerates, that contributes to current flow, that has all the signatures of a thing that exists. The whole is a quasiparticle. To understand how an absence can move, try this. Picture one of those old sliding tile puzzles, the kind with a grid of numbered squares and one square missing. The blank tile, the gap, doesn't move on its own. It has no substance, nothing to push. What moves is always the tiles adjacent to it. One neighboring tile slides into the blank space, and the blank space appears to have slid in the opposite direction. Another tile shifts, and the blank seems to drift again. Watch the puzzle long enough, and you can track the trajectory of the absence as if it were an object. It navigates the board, it goes from corner to corner, and yet at no point did anything move except the solid tiles shuffling to fill the space that was already empty. This is almost exactly what happens in a semiconductor. When an electron jumps away and leaves its empty seat, the electrons around it notice the vacancy. One of them slides in, drawn by the slight imbalance, filling the hole. But now it has created a hole where it was. And another electron fills that hole. And on, a cascade of short shuffles. each one a real electron moving a small distance in one direction, and the pattern of the shuffles, the empty space that propagates through the system, moving in the other direction. The whole travels. It travels as convincingly as any particle, and because it is the absence of a negative charge moving in one direction, it registers on every instrument as a positive charge moving in the opposite direction. Think of a bubble rising through still water. The water doesn't know it's pushing a bubble. Each water molecule simply responds to the pressure around it, sinking slightly as the bubble moves past, rising gently as the bubble moves on. The bubble itself contains nothing. It is a pocket of air, or simply of lower pressure, or of less water. And yet the bubble rises. It has a trajectory. If you put your hand in the water above it, you'd feel it arriving. The bubble is real in every practical sense, not because of what it contains, but because of the coordinated behavior of all the water moving around it. Remove the water, and the bubble vanishes. The bubble is not made of water. The bubble is the pattern of water's behavior. It lives in the relationship between the water molecules, not in any one of them. The whole is the bubble. The electrons are the water. And this quasiparticle, this particle, made of nothing, made of an empty seat, runs every transistor on Earth, every logic gate in every computer, every switching circuit in every phone, every amplifier in every radio, every pixel in every screen, every chip in every piece of modern technology is engineered around two kinds of charge carriers, electrons moving in one direction and holes moving in the other. Semiconductor electronics is not a science of electrons alone. It is a science of electrons and of the coordinated absences of electrons, treated as particles of equal standing, tracked and guided and manipulated with the same precision as anything else physics takes seriously. The whole has an effective mass. The whole has a lifetime. The whole contributes current. It is measured, real, and indispensable, and it is made of nothing at all. Let that be a comfort, somehow, in the quiet of this moment. The devices that run your world are not doing what you probably thought they were doing. They are not just pushing electrons around. They are managing a conversation between something and nothing, between charge and its absence, between the electron and the empty seat it left behind. And the physics of that conversation, the rules that govern holes and electrons and how they move through a crystal, works flawlessly, because the mathematics doesn't care whether the particle is made of matter or made of missing matter. It only cares whether the behavior obeys the rules. And holes do. Now carry this idea one step further, because the phonon was only the beginning of the strangeness, and the whole only one variation on the theme. There is another way the relationship between an electron and its surrounding crystal can produce something that bends the mind quietly. Something you can feel in its oddness, even when you're half asleep, and letting the words wash over you without trying too hard to follow. It has to do with mass. With what the word mass actually means when you look closely at an electron moving through a real solid rather than through empty space. In a physics textbook, the electron has a mass. It is a fixed, known, exact number. The mass of an electron is approximately 9.109 times 10 to the power of negative 31 kilograms, a number so small it resists any intuition. But a number that is nevertheless fixed, universal, the same for every electron in every corner of the universe. Take an electron and put it in a vacuum, in empty space with nothing around it, and if you push it, it accelerates in exactly the way that fixed mass predicts. Newton's old law still holds. Force equals mass times acceleration, and the mass of the electron is what it has always been. Now put that same electron inside a crystal. The crystal is not empty space. The crystal is a periodic, regular structure of atoms and their positive charges, an orderly landscape of electric hills and valleys, a terrain that exerts forces on the electron as it moves. And something remarkable follows from this. The electron moving through the periodic potential of a crystal does not respond to an applied force the way a free electron does. It responds differently, because the lattice is always pushing and pulling on it, and those lattice forces complicate the simple force equals mass times acceleration story in a precise and calculable way. The net result is that the electron accelerates as if it had a different mass, a mass that is not the true vacuum mass, a mass that has absorbed, mathematically, all the effects of the crystal's periodic potential. This is called the effective mass. And it is as real as any other mass, in the only sense that matters. If you apply a known force to the electron quasiparticle moving through the crystal and measure how it accelerates, the number you get is the effective mass. And it is what determines everything about the electron's behavior in that material. The effective mass can be smaller than the true vacuum mass. In some semiconductors, the electrons are lighter than free. They accelerate more easily, respond more quickly, zip through the material as if the lattice were helping them along rather than impeding them. This is part of why gallium arsenide, for instance, has particular electronic properties that make it useful in certain fast devices. The effective mass of its electrons is only a fraction of the free electron mass, and that lightness has real engineerable consequences. But the effective mass can also be larger. The lattice can slow the response, make the electron seem heavier, harder to push, more sluggish, and in some extraordinary materials, the effective mass doesn't just become a little larger, it becomes enormous. These are the heavy fermion materials. The name comes from the fact that electrons are fermions, a category of particle that obeys a particular set of quantum rules about how many can occupy the same state at once. And in these unusual compounds, the fermionic quasiparticles behave as if they are extraordinarily heavy, hundreds of times heavier. In some compounds, the effective mass reaches hundreds of times the free electron mass. In the most extreme cases, in materials like cerium copper silicide, the compound known to physicists by the formula CQ2Si2, the electron quasiparticles can behave as though they are close to 1,000 times heavier than a free electron. The same particle, measured in a vacuum, would have one mass. Measured in this material, it responds as if it weighs 1,000 times as much. This is not a malfunction or an error. It is not an approximation that breaks down under scrutiny. It is the precise, experimentally confirmed behavior of these materials, and it arises entirely from the collective interaction between the electrons and the material's unusual electronic structure, particularly from the way F-shell electrons in the rare earth or actinide atoms that make up these compounds hybridize with the conduction electrons, creating a highly entangled, correlated many-body state. The heaviness is real. It is measured by the way these materials absorb heat, by the way they respond to magnetic fields, by the way their electrons carry current, all consistent with the extraordinary effective mass. The electron inside CQ2Si2 is not a different particle, but it is embedded in a relationship so complex, so deeply entangled with the surrounding quantum state of the material that it moves through the world as if it had borrowed 1,000 times its normal weight from everything around it. And if the effective mass can be larger than the free mass and smaller, you might wonder whether it can be something even stranger. Whether it can be, in some sense, the wrong sign entirely. It can. In certain energy bands, under certain conditions, the effective mass is negative. An electron with a negative effective mass, when pushed in one direction, accelerates in the other. It responds to force backwards. This sounds absurd, and if you encountered it in a vacuum, it would be. But inside a crystal, where the effective mass is not the true mass, but the net result of the electron's interaction with the periodic potential, a negative effective mass has a clean mathematical meaning. It is what happens at the top of an energy band, where the curvature of the energy landscape flips, and the electron finds itself in a region where the lattice forces more than cancel the applied force, reversing the net acceleration. Negative effective mass is part of the theory of semiconductor bands, and it is the foundation for understanding how holes behave. The hole at the top of a filled band has a positive effective mass precisely because it is the quasiparticle that results from removing an electron with negative effective mass, and the two negatives multiply into something sensible. The mass of a quasiparticle, in other words, is not a property of the electron alone. It is a property of the electron in conversation with everything around it. It is an emergent property of the relationship, not an intrinsic property of the thing. And this, again, is the refrain you'll hear in every variation of this story, the note that runs through every quasiparticle like a thread. The whole is doing something the parts cannot do alone. The electron brings its true mass to the party, but the party gives it a completely new one. Breathe that in slowly. The same electron, in different rooms, weighs different amounts. Not because it changes, but because what it means to have a mass in a material depends on the material. The electron is always the electron. But the quasiparticle it becomes, the entity the physics of the solid makes available, is shaped by the context it inhabits. Mass is not the private property of the electron. It is a co-production, a collaboration between the electron and the crowd. Now let's follow one particular electron as it does something it always does and has always done, as it simply moves through a material. Not a metal this time, not a semiconductor, but an ionic crystal. A compound in which the atoms carry electric charges of their own, like sodium and chlorine bound together in table salt, or the slightly more exotic compounds studied in polaron research. And in this material, as the electron moves, something begins to happen. The electron carries a negative charge, and as it passes through the crystal, that negative charge pulls on the positive ions nearby and pushes away the negative ones. The lattice is not rigid in a perfect mathematical sense. It is elastic, it responds, it bends and distorts. As the electron moves, it deforms the crystal around itself. The positive ions lean slightly inward, drawn toward the passing negative charge. The negative ions lean slightly away. A small, persistent dent forms in the fabric of the crystal, following the electron wherever it goes, a little wake of distortion that the electron itself creates and drags along behind it. This is the situation Lev Landau considered in 1933. He was working on a problem that had been nagging at physicists studying the electrical properties of ionic crystals. The observation that electrons in these materials moved far more sluggishly than anyone expected, far more slowly than the simple free electron model predicted. The electron should have been light and quick. Instead, it crept. Something was slowing it down. And Landau asked the natural question, what if the electron isn't moving alone? His insight was this: the electron and its surrounding distortion don't separate. They can't, because the distortion is caused by the electron's presence and disappears the moment the electron leaves. The electron creates the dent. The dent follows the electron. The electron plus dent form a single unit. And this unit, this composite of the electron and the cloud of lattice distortion it drags, is heavier than the electron alone. The electron has to carry its own disruption. It has dressed itself in a cloud of displaced atoms, and the cloud makes it slower, harder to accelerate, effectively more massive. The electron, in this context, becomes a polaron. The name comes from polarization, from the way the electron polarizes, or electrically distorts, the crystal around it. Landau introduced the concept and, working later with Solomon Pekar, developed the mathematical description of the strong coupling limit, the case where the electron is so tightly bound to its distortion cloud that the two can barely be separated even in theory. The polaron is the electron plus its burden, moving together as one. What makes the polaron particularly beautiful, as quasiparticles go, is how vivid the image is. There is something almost mythological about it, the electron, as a figure moving through a world that yields to its presence, leaving a trail of displacement and unable to shed the trail, no matter how far it goes. The distortion is not passive. It is not just a byproduct. It is constitutive. It is part of what the electron in this material actually is. Strip away the distortion and you no longer have a polaron, you have a bare electron, a different, lighter thing that the ionic crystal simply does not permit to exist for long in its natural state. The polaron is the stable, natural form that an electron takes in this environment. The crystal insists on it. And the weight gained is not trivial. In strongly ionic materials, the polaron mass can be many times larger than the free electron mass. The electron arrives heavier than it left, as if the journey through the crystal has accumulated something onto it. The way a stone rolling through wet earth accumulates a coating of mud and arrives at the bottom of the slope transformed, increased, slowed. The mud was never part of the stone. But the stone plus mud is the thing you have to push. Sleep soft, this is the image to carry into the dark, the electron, moving through the crystal, gathering its cloud. Not burdened exactly, because burden suggests the cloud is a hardship, and in physics there is no judgment in it. The cloud is simply the electron's relationship with the material it inhabits, made visible and physical. The polaron is what emergence looks like from the electron's point of view. Its properties, its mass, its speed, its behavior under an applied force emerge from the conversation between the electron and the crystal, not from the electron alone. Landau and Pekar formalized the mathematics of the strongly coupled polaron, and later theorists extended the work to the weakly coupled case. And the polaron has been studied in materials ranging from organic semiconductors to transition metal oxides to the strange compound systems where unusual electronic behavior concentrates. Polarons matter in the physics of organic solar cells, in the understanding of colossal magnetoresistance, a phenomenon where certain materials change their electrical resistance dramatically in response to a magnetic field, and in the behavior of electrons in the complex oxide materials that have become one of the most active research areas in condensed matter physics. Every time an electron moves through an elastic ionic material and drags its distortion along, the polaron is there, doing its quiet work, arriving heavier than it started. And this, gently, is the third way that the emergence idea shows its face in the catalogue of quasiparticles. The phonon showed it in sound, collective vibration, indivisible from the whole. The whole showed it in absence, a particle, made of nothing, behaving as something. The polaron shows it in burden, a particle shaped by the world it inhabits, carrying that world's response in its mass. And now there is one more variation on this theme to hold before this part of the story rests. One that takes the ideas of the whole and the electron and brings them together into something that is perhaps the most intimate and symmetrical of all the quasiparticles we have met so far. Something that carries energy without charge. Something that is, in a certain poetic and physically precise sense, an electron in orbit around its own absence. When an electron in a semiconductor absorbs enough energy to leap out of the filled band and into the empty one above it, two things happen simultaneously. The electron ascends, it moves to a higher energy state where it can carry current, where it has room to roam, where it is free in the way a conduction electron is free. And the whole descends, or rather appears, the empty seat the electron left behind, that positive quasiparticle made of an absence, sits now in the filled band below. The electron is above, the whole is below. They are separated by the energy gap that the electron crossed. But they are not strangers to each other. The electron carries a negative charge. The whole carries, in effect, a positive charge, and opposite charges attract. The electron and the whole, separated by the energy gap, pull on each other. They feel each other across the distance. And if the conditions are right, if the temperature is low enough, if the material is the right kind, if the electron doesn't immediately scatter or recombine, they can fall into orbit around each other, not around a nucleus, the way an electron orbits an atom, around each other. The electron and the whole, circling a common center, each held in place by the attraction to the other, each orbiting the other's charge, the way two dancers orbit the space between them. This is the exciton. The name comes from the Greek for excitement or excitation. The thing is born from excitement, from the excitation of an electron. And its structure is strikingly like the structure of hydrogen, the simplest atom. One negative charge orbiting one positive charge, bound by electrostatic attraction, occupying a set of quantized energy levels that can be calculated with the same mathematics Niels Bohr used for hydrogen more than a century ago. The exciton is, in the language of atomic physics, a hydrogen-like system, except that neither the electron nor the whole is a nucleus. The electron is not a proton. The whole is not matter at all. It is the quasiparticle of absence. And together, the electron and the absence form a thing that behaves like an atom. It is neutral. The negative charge of the electron and the positive charge of the whole cancel exactly. The exciton carries no net electric charge. It cannot therefore carry electrical current in the way a free electron or free hole can. It has no charge to push through a circuit. But it can move. It can drift through the crystal, carrying its energy with it, transporting the excitation from one place to another without transporting any charge at all. It is a carrier of energy that is charge neutral, and this peculiar property is at the heart of why excitons matter so profoundly in devices that convert light into electricity or electricity into light. In a solar cell, in the photovoltaic panels that sit on rooftops and convert sunlight into electrical power, the first step when light strikes the semiconductor is not the production of free electrons and free holes. The first step is the production of excitons. A photon is absorbed, an electron jumps the gap, and the electron-hole pair that forms is often initially bound together as an exciton, orbiting each other rather than flying free. For the solar cell to generate electrical current, something must happen to break that bond, to pull the electron and the hole apart so each can go its separate way, electron toward one electrode and hole toward the other. This is the purpose of the internal electric field at the junction in a solar cell, to exert enough force to separate the exciton, to overcome the binding energy, to free the carriers and let them drive a current. Understanding excitons and how they form and split is central to designing more efficient photovoltaics. And in an organic light-emitting diode, the technology inside the glowing screens of many modern televisions and smartphones, the process runs in reverse. Electrons and holes are injected into the organic semiconductor material from opposite electrodes. They drift toward each other. They meet somewhere in the middle of the material, and instead of passing through each other or scattering, they can combine, falling into an orbiting pair, forming an exciton. And then the exciton does what a bound electron-hole pair will eventually do when it cannot be sustained: it recombines. The electron falls back down into the hole. The orbit collapses. The energy difference between the excited state and the ground state is released as a photon of light. The screen glows, not because electrons are jumping from one electrode to the other and producing light along the way in some simple direct fashion, but because electrons and holes are meeting in the middle of the material, forming the temporary orbiting partnership of the exciton, and then releasing their energy as light when the partnership ends. The OLED screen is, in this sense, a machine that produces excitons by the trillions per second and harvests the light they emit when they die. Its color is determined by the energy of those excitons, by the gap between the excited and ground states of the organic semiconductor used, and tuning that color means engineering the exciton's energy, which means engineering the quantum chemistry of the material it lives in. The exciton is, like all the quasiparticles we have visited, not visible. You cannot isolate one and hold it up to the light. It has a lifetime, sometimes extremely short, measured in fractions of a nanosecond, the exciton forming and recombining faster than any conscious process can track. And it exists only in the semiconductor material, in the relationship between the electron and its own absence, bound by the attraction between a thing and the empty space it left behind when it climbed to somewhere higher. There is something almost impossible not to find moving about this, in the quietness of the late hours. An electron and the hole it made when it jumped, these two, the particle and its absence, the charged thing and the nothing it left behind, circling each other through the crystal as if neither one knows quite how to go entirely separate ways. As if the jump itself, the departure of the electron from its seat, left a kind of bond between the traveller and the vacancy, a gravitational sentiment woven into the mathematics of attraction. They orbit each other for a while, neutral and mobile, carrying between them the energy of the original excitation, neither quite free. And then they recombine, and the energy passes on into the world as light, or heat, or another excitation somewhere else, and the pairing is over. This is what quasiparticles do. They form, and they carry, and they recombine. They hold energy in a shape for a while, in the borrowed form of a particle, and then they let it go. The whole taught us that absence can carry charge. The polaron taught us that the electron can be reshaped by the world it inhabits, made heavier by the distortion it creates. The exciton teaches us that two quasiparticles, the electron and the hole, the presence and the absence, can find each other and, for a brief interval, become something together that neither one is alone. A neutral, mobile carrier of energy, a hydrogen atom made of one real thing and one empty space. And all of this, the whole, the effective mass, the polaron, the exciton, all of it is still only one region of the territory. The quasiparticle catalogue is wider than this. There are quasiparticles born not from electric charge, but from magnetism, from the collective alignment and misalignment of spins. There are quasiparticles born from the sloshing of the entire ocean of conduction electrons at once, thousands of billions of electrons moving together. And this collective sloshing is what colors medieval glass and makes gold nanoparticles scatter ruby red. There are quasiparticles that are half light and half matter, that exist on the boundary where a photon and an excitation in a crystal become so entangled that neither the photon nor the excitation can be said to exist independently anymore. And there are quasiparticles of a kind so strange that their existence required a new category of particle altogether. Particles that are neither fermion nor boson. Particles that remember in a quantum mechanical sense, having been swapped with one another. Particles that can store information in their braided histories rather than in any local physical state. Each of these carries the same spine. Each one is an instance of the same emergence idea. The same deeper principle that runs through the whole story like a thread. The whole is doing something the parts cannot do. The material is hosting entities that no single atom, no single electron, no single spin could ever produce alone. The quasiparticle is the collective behavior of a vast number of pieces, behaving so coherently, so regularly, so rule-obeying that the mathematics of quantum mechanics has no choice but to grant it the status of a particle in its own right, not a metaphor. Not an approximation that breaks down under pressure. A real thing, in the only sense that real things get to be real. It carries momentum. It has energy. It scatters off other things in exactly the way a particle should scatter. It registers in detectors, and it allows physicists to calculate the answers to real questions. What temperature does this material conduct heat at? What frequency of light does this material absorb? How does this material respond to a magnetic field? Answers that match experiment, that let engineers build solar cells and old screens and semiconductors and all the rest of it. Rest now with that word, the one that has been quietly present since the beginning but hasn't been named outright yet. The word that the physicist Philip W. Anderson reached for in a famous essay he published in 1972, a short piece called More is Different, that is, in some ways, the philosophical spine of everything this night's journey is made of. Emergence, the idea that at each level of complexity, each scale of organization, entirely new properties appear that you could not have predicted or read off from the level beneath. That the behavior of the whole is not simply the sum of the behaviors of its parts, but something qualitatively different, something that requires its own language and its own laws. A single water molecule is not wet. Wetness is not a property of water molecules. It is a property of very large collections of them, in a particular arrangement, behaving in a particular collective way. You cannot point to the molecule that is responsible for wetness. Wetness is in the relationship between the molecules, not in any of them. And the quasiparticle is emergence made precise and mathematical. It is the moment when the collective behavior of a crowd of electrons or atoms or spins becomes so coherent, so particle-like in every quantifiable sense, that the physics says, treat it as a particle. Not pretend, not as a convenient fiction. Treat it as a particle, because doing so gives you correct, predictive, exact answers, and no alternative approach is available that works as well. The quasiparticle is not lesser than a real particle. In the context of the material that hosts it, it is all the particle there is. Let the lattice hum. Let the electrons drift and the holes follow. The polarons accumulate their burden. The excitons form and orbit and recombine. The solid world you inhabit, the metals and semiconductors and insulators and the organic compounds that make your screens glow, all of it is full, in the language of quantum mechanics, of these patterns, these coordinated motions, these collective behaviors that have earned their particle names and their places in the equations. You cannot see them. You cannot hold one. But they are in there, living in the relationships, doing the work. The question that opened at the very beginning of this night, if the particle isn't in the parts, where does it live, has begun, gently, to answer itself. It lives where all relationships live. Not in any single element of the conversation, but in the space between them. In the give and the response, in the disturbance that one thing makes in another, in the empty seat and the orbiting partner, in the electron heavier with its world's weight, in the bound pair that carries energy across the crystal toward the light. And there is more still to come, quieter and stranger, and more beautiful in its strangeness. Because the quasi-particle story does not end with charge and mass and the behavior of single electrons. It opens, further into the physics of spin, of collective magnetic ripples, of whole oceans of electrons sloshing at frequencies that color glass and heal ancient mysteries. Into the question of what happens when the coupling between matter and light becomes so strong that the two cannot be separated. Into the liquid that flows forever and climbs its own walls. Into the deepest and most unnerving corner of the story, where the quasiparticles are no longer fermions or bosons, but something the universe had apparently been keeping in reserve. Something that only appears when you confine the world to 2 dimensions and let the electrons organize themselves into the most extraordinary collective state that quantum mechanics permits. But that is ahead, in the darker hours still to come. For now, carry the 4 figures with you as the narration turns, the whole, the absence that carries charge, the quasi-particle with its borrowed, malleable, sometimes enormous, sometimes reversed mass, the polaron, the electron weighted by its own passage through the world, and the exciton, the particle made of a particle and a not particle. Orbiting each other across the energy gap, neutral and mobile and briefly, tenderly, together, the crystal is patient. The electrons are countless. And the patterns they make, the quasi-particles they give rise to, the emergent entities that live in their collective behavior, are stranger and more varied and more quietly wondrous than any single atom, alone and indivisible, could ever be. Turn your attention now to a different kind of wave, not the vibration of atoms pushing against each other, not the ripple of charge that we trace through the exciton, but something quieter, something magnetic, something that moves not through position, but through alignment. Every atom in a magnetic material carries a tiny magnetic moment. You can think of it as a compass needle impossibly small, built into the atom itself, pointing in some direction, up, down, slightly tilted, angled, and in a magnet, these needles do not point randomly. They agree. They coordinate. Billions of atomic compass needles, all aligned in the same direction, their agreement creating the field you can feel tugging at iron filings, the field that holds a note to a refrigerator door. That collective agreement is what makes a magnet, and it is, in its own way, as remarkable as anything else we have traced through these crystals tonight. But now disturb one of those compass needles, tilt just one slightly out of alignment. What happens? If the needles were truly independent, if each atom's magnetic moment were its own private affair with no relationship to its neighbors, nothing would happen. The tilted needle would stay tilted. The other needles would not notice. But they are not independent. Each atom's magnetic moment interacts with the moments of the atoms immediately around it through quantum mechanical forces called exchange interactions. And so when one needle tilts, it nudges the next one slightly. And that needle nudges the one beyond it. And so the disturbance propagates, not as a single displaced atom moving through the crystal, but as a wave of tilt, a ripple of misalignment spreading outward from the original perturbation, like a slow wave moving across a field of grass when the wind passes through it. This is a spin wave. The individual atoms stay in place. Each compass needle merely tilts by a small angle, and then, as the wave passes through, returns, what travels is the pattern of tilting, the coordinated disturbance, the wave of misalignment moving through the agreement of the collective. And here, exactly as we have seen with sound in the phonon, quantum mechanics insists that this wave's energy does not come in just any amount, it comes in discrete packets. The minimum unit of excitation of a spin wave is a single quantum, and that quantum has a name. Felix Bloch gave it that name in 1930. He was 24 years old and working out the quantum mechanical theory of magnetism, and he found through the mathematics that these spin waves were quantized, that you could not have half a spin wave quantum any more than you could have half a photon of light. The smallest unit of a spin wave became known as the magnon. The magnon is a quasiparticle of spin. It carries the quantum of angular momentum we call spin. The same spin that makes electrons fermions, the same spin that gives a magnetic moment its direction. But it carries no electric charge. The magnon is magnetically meaningful and electrically invisible. It cannot push a current. It cannot be steered by an electric field. It moves through the magnetic texture of a material, propagating its wave of tilting spin, and it interacts with other magnons and with other quasiparticles, and it scatters and decays. And it carries with it a well-defined energy and momentum, and in every formal sense it is a particle. Its existence was not a theoretical curiosity for long. Neutron scattering experiments confirmed that magnons were real excitations, measurable, with energies that matched Bloch's predictions, and the physics of magnons has been refined and deepened over the nearly century since. Notice what the magnon is not. It is not a magnetic north pole moving through the crystal. It is not a small magnet flying between atoms. It is a wave of coordinated change in the orientations of billions of atomic moments, and the one indivisible quantum of that wave is the magnon. As with the phonon, you cannot find the magnon inside a single atom. Isolate one atom and the magnon vanishes. It exists only in the relationship between atoms, in the way they are coupled, in the texture of their agreement, and how that agreement can be disturbed, and how the disturbance chooses to travel. There is something restful about this idea. The magnon is disturbance itself, quantized. It is not a thing moving, but a motion that has become a thing. And here is why physicists today are paying close attention. Electrons, as they move through a conductor carrying electric current, are constantly scattering, bouncing off lattice vibrations, off impurities, off each other, and every scattering event dissipates energy as heat. This is resistance. This is why your phone gets warm and why data centers consume enormous amounts of power just to keep their chips from overheating. The heat is the cost of moving information on the back of electric current. Magnons do not carry charge. When magnons scatter, the energy they carry does not convert to heat through the same electrical resistance mechanisms. The field now called magnonics, the study of information carried by spin waves rather than electric current, is exploring whether the logic of computation can be encoded in magnons instead of in the movement of electrons. Whether a signal carried as a wave of spin could pass through a material and do work and be processed and be read out without generating the heat that plagued its electrical cousin. The magnon represents a road not yet fully travelled, a different architecture for computation built on a wave that the magnet's atoms are always already prepared to carry. Close your eyes a moment and think of the magnetic material at rest, its billions of tiny needles all aligned, the quiet agreement of the collective. The magnon is what happens when something breaks into that agreement, briefly and precisely, and the disturbance moves through like a thought passing through a dreaming mind. Now move from spin to charge, from the magnetic sea to the electric one. Inside a metal, copper, gold, silver, aluminum, any good conductor, there is something often called the electron sea or the electron gas, or more formally, the conduction band. The outermost electrons of the metal atoms have detached from their parent atoms and are free to roam through the whole material. They are not bound to individual atoms, they belong to the metal as a whole, and there are an enormous number of them. In a cubic centimetre of copper, there are on the order of 10 to the 22nd free electrons, that is, 10,000 billion electrons, freely mobile, constantly moving at high speed, even at room temperature, a dense and churning ocean of charge. This ocean has its own collective dynamics. Just as water in a tank can slosh, the whole body of liquid shifting back and forth under the right conditions, the entire sea of conduction electrons in a metal can oscillate collectively. All of them, or a large fraction of them, shifting one way and then back, driven by their mutual electrical repulsion and by their attraction to the positive background of the metal ion cores they move through. This collective oscillation of the electron sea is real, and it is measurable, and it has a characteristic frequency determined by the density of electrons and the effective mass of those electrons. And because quantum mechanics governs the electron sea just as it governs everything else at this scale, the energy of this collective oscillation is quantized. The smallest quantum of a collective oscillation of the electron gas is called a plasmon. The word comes from plasma, the physicist's term for a gas of charged particles, and the suffix is the same we have used throughout, the marker of the quantum, the badge of the collective, the signal that here too a wave has become a particle. The plasmon is the quantum of the collective charge oscillation of the electron sea. Now plasmons in the bulk of a metal throughout the entire volume exist at very high frequencies. The energy needed to set the whole electron gas oscillating is large, corresponding to ultraviolet light frequencies, and for many practical purposes, bulk plasmons are not easily excited and not directly observed in everyday optics. But something more subtle and more beautiful happens at the surface of a metal, at the boundary where the metal ends and air or glass or another medium begins. At a surface, the collective oscillation of electrons can become coupled to light, to electromagnetic waves, in a very particular way. The oscillating electron density at the surface drives an oscillating electromagnetic field that extends a short distance out from the surface into the surrounding medium, and the electromagnetic field in turn drives the electron oscillation, and the two become locked together. The result is a surface plasmon polariton, a quasiparticle that travels along the surface of the metal, part oscillating electron density, part electromagnetic wave, confined to the interface. It is a wave that runs along the skin of the metal, neither fully inside nor fully outside. Surface plasmons are exquisitely sensitive to the size and shape of the metal structure they ride. When the metal is not a flat surface but a tiny sphere, a nanoparticle much smaller than the wavelength of visible light, the surface plasmon cannot simply travel along a surface. It is confined. The oscillation of electrons is forced into the geometry of the sphere. And the sphere has its own resonant frequencies at which the electron oscillation and the light it couples to are perfectly matched. At those resonant frequencies, the nanoparticle absorbs and scatters light with extraordinary efficiency. And the resonant frequency, the color of light that the nanoparticle interacts with most strongly, depends on the size and shape of the particle and on the material. For gold nanoparticles of a particular size, the plasmon resonance falls in the green and blue portions of the visible spectrum, which means that gold nanoparticles absorb green and blue light and scatter red light, which means that a medium seeded with tiny gold nanoparticles will appear to human eyes a deep, rich red. This is why the Lycurgus cup is the Lycurgus cup. The Lycurgus cup is a Roman glass artifact from the 4th century, now held in the British Museum. It is one of the most technically remarkable objects to survive from the ancient world, not because of its artistry alone, but because of what it does with light. When you hold the cup with light shining on it from the outside, light reflected off its surface, it appears a murky green. When you hold a light source inside the cup and look through the glass, it glows a deep, translucent red, like a gemstone, like a lamp made of garnets. For centuries after it was made, no one in the modern world knew why. The cup was admired and puzzled over, but the mechanism was a mystery until electron microscopy in the 20th century revealed what the Roman craftsmen had worked into the glass, almost certainly without understanding the physics they were exploiting. Embedded throughout the glass are nanoparticles of gold and silver, roughly 70 nanometers across, distributed through the material at an extraordinary level of uniformity. The Roman glassmakers had, through some now unknown technique, created a colloidal suspension of metal nanoparticles in glass. And those nanoparticles scatter red light and absorb other wavelengths because of surface plasmon resonance. Because of the collective oscillation of the conduction electrons within the gold and silver particles, tuned by the particle's geometry to interact resonantly with red light. The same effect colors much of medieval stained glass. The deep ruby red of cathedral windows was achieved with gold dissolved into the molten glass in the form of colloidal particles, creating the same plasmonic scattering that made the Lycurgus cup glow. The medieval craftsmen who mixed gold into their glasswork were encoding quantum collective behavior into stone and light centuries before the word electron was coined, millennia before Landau or Bloch or BCS. This is the plasmon, then, the quantum of the electron sees collective sloshing, able in its surface form to be tuned by geometry, able to scatter specific colors of light, able to leave its signature in objects made by hands that could not have named what they were doing. The plasmon is not a particle in the way an electron is a particle. It is the whole ocean moving at once, reduced to its minimum quantum of motion. And now something even stranger, because we are about to meet a quasiparticle that is not made of electrons at all, or at least not made only of electrons. We are about to meet something that is made of two things simultaneously, two things that seem so unlike each other that their union feels almost like a violation of category. something that is at the same time and inseparably, both light and matter. Light and matter are, in ordinary experience, opposite kinds of things. Matter is the stuff you can hold. It has mass, it occupies space, it pushes back. Light is the thing that passes through space and bounces off matter and travels at the speed that sets the universe's speed limit. Light and matter interact. Light can be absorbed and emitted, reflected and refracted. But they are not usually thought of as the same thing. They are the observer and the observed, the signal and the receiver. But in quantum mechanics, when light and matter interact, the distinction between them can become less clean than it appears. Under the right conditions, a photon, a quantum of light, can couple so strongly to a quantum excitation of matter that the two cease to be separately meaningful things. The coupling becomes stronger than either can resist, and what you have is no longer a photon sometimes coupled to an exciton, or an exciton occasionally absorbing a photon. What you have is a new entity, a single quantum state that is partly photon and partly matter excitation, inseparably blended. This is a polariton. The specific kind that has attracted the most experimental attention is the exciton polariton. You will remember the exciton from the previous hour of this narration, the bound pair of an electron and the hole it left behind, orbiting each other across the energy gap of a semiconductor, carrying energy without carrying net charge, like a tiny neutral hydrogen, like atom made of one particle and one absence. Excitons have a characteristic energy, the energy of their bound state, and they can absorb and emit light at that energy, coupling to photons. In a specially designed semiconductor structure, a thin slab sandwiched between reflecting surfaces, forming what physicists call a microcavity, photons can be trapped. The mirrors keep them bouncing back and forth. An exciton sitting in the semiconductor can couple to a trapped photon. And if the coupling is strong enough, the photon is absorbed and a new exciton is created and the photon is re-emitted, and the cycle repeats so rapidly that the exciton and the photon cannot be said to be separate things at all. The quantum superposition of photon here and exciton there becomes a single stable state. The polariton. The polariton inherits properties from both parents. From the photon, it inherits lightness, a very small effective mass, much smaller than the excitons, which makes it highly mobile and able to travel at high speeds. From the exciton, it inherits the ability to interact with matter, to scatter off other excitations, to feel the presence of the crystal it lives in. The polariton is social in a way the photon is not. It can collide and exchange energy with other polaritons and with other quasiparticles, and here the story takes a turn that feels, in the quiet of this late hour, almost too beautiful to be laboratory physics. Because polaritons are bosons, or more precisely, because they inherit their statistical character partly from the bosonic photon they are partly made of. They obey Bose-Einstein statistics. And bosons, at low enough temperatures or high enough densities, can all fall into the same quantum state at once. They can condense. They can undergo Bose-Einstein condensation, the state in which thousands or millions of particles lose their individual identities and become a single collective quantum thing, described by one wave function, moving in perfect unison. Bose-Einstein condensation of atoms was first achieved in the laboratory in 1995 at temperatures within a fraction of a degree of absolute zero, using elaborate laser cooling and magnetic trapping, a profound achievement requiring the coldest conditions humans had ever made. But exciton polaritons, because of their extraordinarily small effective mass, many times lighter than an atom, can condense at much higher temperatures. Research groups, including work synthesized and reviewed by Deng, Haug, and Yamamoto in 2010, demonstrated polariton condensation at temperatures far above what atomic systems require, in some cases approaching room temperature in specially chosen materials. A condensate of something that is part light, part matter, forming not at the coldest edge of the achievable, but at conditions far more accessible. What does it mean for a polariton to condense? It means that a macroscopic number of these light-matter hybrids all enter the same quantum state, all moving with the same momentum, all described by a single coherent wave function. The photons they are partly made of all point in the same direction. The microcavity begins to emit laser-like light, not because there is a gain medium pumping energy in, as in a conventional laser, but because the polaritons have spontaneously organized themselves into coherence. The laser-like emission is a consequence of the condensation, not its cause. Rest with this for a moment. A thing that is neither fully matter nor fully light, inheriting the personality of each, forming a condensate, a single unified quantum state shared by many, at temperatures where ordinary quantum condensation is not supposed to happen. The polariton sits at a boundary the physics of isolated systems never quite reaches. It is an entity that exists only because matter and light agreed, in a particular geometry and at a particular coupling strength, not to be separate things. Every quasiparticle we have visited tonight lives somewhere on that spectrum. From the almost ordinary, like the phonon's quantized sound, through the counterintuitive, like the whole's positive charge made from absence, to the deeply strange, like the polariton's hybrid identity. The magnon, the plasmon, the polariton. Each one is the collective behavior of a specific aspect of matter, quantum mechanized into a particle-like object with its own properties and dynamics. And each one is, in a precise sense, less strange than it first appears, because each obeys the rules, each can be measured, each appears reliably in the right conditions, and behaves consistently with what the theory predicts. But we have not yet reached the deepest place in this journey. We have not yet followed the electron all the way to the discovery that changes the story of resistance itself. Consider again the electron's dilemma inside a metal. It is one particle in a sea of 10 to the 22nd, all carrying negative charge, all repelling each other through the electromagnetic force. Electrons repel. This is not a gentle suggestion, like charges repel through an inverse square force that grows stronger as the distance decreases. Two electrons close together push each other apart with a force that has no natural cutoff. Everything we know about the electron insists that two electrons cannot be partners. They are adversaries, they push each other away, and they always have. Which is why the thing that happens in a superconductor is so difficult to believe the first time you hear it. In 1908, the Dutch physicist Heike Kamerlingh-Onnes succeeded in liquefying helium, reaching temperatures within a few degrees of absolute zero. With this new tool, he began measuring the electrical resistance of metals at very low temperatures. In 1911, working with mercury cooled to about 4 Kelvin, 4 degrees above absolute zero, he found something that had no right to be there. The resistance of mercury did not decrease gradually as the temperature fell, as it had in every material anyone had ever measured. At 4 Kelvin, the resistance did not merely decrease. It vanished completely, to unmeasurably below anything his instruments could detect. The mercury was conducting electricity with no resistance whatsoever, a thing that should, according to everything known about electrons scattering off lattice vibrations, be impossible. Onnes called it superconductivity. The phenomenon would be measured in other materials over the following decades. Lead, aluminum, tin, niobium, material after material, cooled below its own characteristic critical temperature, underwent the same transition. The resistance went to zero. Currents injected into a superconducting ring and left alone circulated for years without measurable decay. The phenomenon was real, reproducible, and utterly unexplained for nearly half a century. The explanation arrived in 1957 from three physicists at the University of Illinois, John Bardeen, Leon Cooper, and John Robert Schrieffer. Their theory is known as BC's theory, from the initials of their names, and it earned them the Nobel Prize in Physics in 1972. And the explanation, when it came, required introducing what is perhaps the most counterintuitive quasiparticle of this entire narration, the Cooper pair. Here is the central fact of BC's theory. In a superconductor, below the critical temperature, electrons pair up. Electrons, which repel each other, which are adversaries, which carry the same sign of charge and push each other away, form bound pairs. And these pairs condense, all falling into the same quantum state, forming a coherent collective entity that flows through the material without any mechanism for resistance to grab onto. The question is how? How do electrons that repel each other manage to form a pair? The answer lies in the lattice, in the crystal of positive ions that the electrons move through. An electron, as it moves, carries its negative charge, and the positive ions of the lattice are attracted to that charge. Very slightly, almost imperceptibly, the ions in the vicinity of the passing electron are drawn toward it, displaced from their equilibrium positions by a tiny amount, creating a region of slightly enhanced positive charge in the electron's wake. The electron has left a dent in the lattice's positive background. The electron moves on. The dent persists for a short time. The lattice takes a while to relax back to its undisturbed arrangement, a time set by the speed of lattice vibrations, on the order of something like 10 to the negative 13th seconds. Long enough for a second electron arriving in the vicinity to be attracted to that lingering enhancement of positive charge. The second electron is drawn ever so slightly toward where the first electron was, and through this mechanism, electron 1 distorts the lattice. The distortion persists briefly. The lingering distortion attracts electron 2. The two electrons become weakly correlated, weakly attracted, weakly paired. You can translate this into quasiparticle language. The first electron emits a phonon, a quantum of the lattice vibration that the displacement of ions represents. The second electron absorbs that phonon. The two electrons exchange a virtual phonon and, in doing so, feel a weak, attractive interaction that, in the conditions of a superconductor, is just strong enough to overcome their direct electromagnetic repulsion. The phonon is the mediator, the lattice is the matchmaker, and the electron pair that forms through this phonon-mediated attraction is the Cooper pair. Leon Cooper showed in 1956 that even a weak attractive interaction between electrons at the Fermi surface, the boundary in energy space that separates the occupied electron states from the empty ones, would lead to the formation of bound pairs, and that the energy of the paired state was lower than the energy of the unpaired state. Cooper pairs, unlike excitons, are not localized objects orbiting each other over short distances. They are spread out. The two electrons in a Cooper pair may be separated by hundreds of nanometers or even micrometers, an enormous distance on the atomic scale, with thousands of other electrons occupying the space between them. And yet, they are correlated. Their quantum states are linked. What happens to one's momentum is reflected in the others. The truly decisive step was taken by Bardeen, Cooper, and Schrieffer together. They showed that the Cooper pairs do not exist in isolation, that all the Cooper pairs in a superconductor condense simultaneously into a single coherent quantum state, described by a single many-body wave function. Every pair, from one end of the material to the other, participates in the same quantum state. The pairs are bosons, 2 electrons, each with spin 1/2, combined to give a total spin of 0 or 1, making the pair an integer spin particle, a boson, and bosons condense. All the Cooper pairs, the entire superfluid of paired electrons, enters the same quantum ground state. And here is where resistance disappears, and the reason is worth settling slowly. Resistance in an ordinary conductor arises because electrons scatter. They hit lattice vibrations, phonons, they bounce off impurities, they collide with defects. Each scattering event changes an electron's direction and speed, converting its organized forward momentum into random thermal energy which manifests as heat. The resistance is, in a sense, the cost of the electron being an individual, being able to scatter independently, being steered off course by the obstacles in the lattice. In a superconductor below the critical temperature, the condensed Cooper pair state is fundamentally different. The pairs are all in the same quantum state, they are all described by the same wave function, spread coherently through the whole material. To scatter one pair would require breaking the coherence of the entire condensate. An individual phonon or impurity does not have enough energy to do that. The condensate moves as a whole, and the disturbances that would scatter individual electrons are simply too small to deflect it. The current flows forward, and there is nothing with sufficient leverage to redirect it. The resistance is not reduced. It is 0, not approximately 0, not measurably very small, exactly, definitively 0. The Cooper pair is a quasiparticle made of 2 electrons and the phonon-mediated attraction between them. It is not a fundamental particle in any elementary sense. Its identity is entirely a product of the lattice and the particular quantum statistics of electrons, and the temperature being low enough for the pairing to survive thermal disruption. Warm a superconductor above its critical temperature, and the thermal agitation breaks the pairs apart. The condensate dissolves. The electrons revert to individual status. The resistance returns. There is a critical temperature for each superconductor, 4 Kelvin for mercury, 9 Kelvin for niobium, about 90 Kelvin for some copper oxide materials discovered in the 1980s. The so-called high-temperature superconductors, whose mechanism is still not fully settled by theory. Below the critical temperature, the pairs can form, and the condensate can maintain its coherence. Above it, thermal energy is too large and too random, and pairing is not stable. The Cooper pair has a lifetime measured against temperature. It exists as long as the cold permits. In this way, the Cooper pair shares something with every quasiparticle we have encountered tonight. It has a lifetime. It exists under specific conditions. It is a collective phenomenon, not a fundamental object. And within those conditions, it is as real as anything physics knows how to be real. It carries charge, it carries momentum, it determines the macroscopic behavior of matter. It is the entity whose condensation makes superconductivity possible. The BC's theory, the theory of Cooper pairs, was described by Bardeen, Cooper and Schrieffer in a paper published in 1957. And it stands as one of the great theoretical achievements of 20th century physics, a complete quantitative account of a macroscopic quantum phenomenon derived from first principles, from the microscopic interaction of electrons and phonons. When the Nobel Committee awarded them the prize in 1972, Bardeen was receiving his second Nobel Prize in physics. The first had been for the invention of the transistor, which, as you will remember, runs on holes, the other great quasiparticle of the semiconductor. 2 Nobel Prizes, 2 quasiparticles, 1 physicist. Let that sit for a moment. The transistor, the fundamental unit of all modern computation, the device in every processor, in every computer and telephone and sensor on Earth, works because a hole, an absence of an electron in a nearly full band, behaves as a positive charge carrier and can be controlled with electric fields. And the superconductor, the material that conducts electricity with zero loss, that expels magnetic fields from its interior, that levitates magnets and enables MRI machines, and may one day carry electrical power across continents without dissipation, works because electrons pair through phonon exchange and condense into a collective quantum state. The same field of physics, the same underlying emergence, the same idea that collective behavior creates new particles the individual parts could never be. Think of the Cooper pair again. 2 electrons, each alone a thing that pushes away every other electron, finding through the intermediary of the lattice a way not to push but to couple. The lattice absorbs the repulsion, repackages it as an attraction, hands the electron a partner. The material has changed the rules of the interaction, and in changing the rules, it has created a new kind of object that cannot exist outside the material, that would be nonsensical in empty space, but that inside the solid is as stable as anything can be at temperatures where the thermal disruption is kept quiet. This is, in miniature, the whole story of quasiparticles. The material is not merely a passive background through which electrons move. The material is a participant. It changes what the electrons are. It lends them new masses, new partners, new collective identities. It converts their vibrations into phonons, and their spin disturbances into magnons, and their charge oscillations into plasmons, and their pairings into Cooper pairs. The solid state is not a container holding particles. It is a system that makes new ones, that takes the particles it began with, and through the sheer fact of their collective presence and their collective interactions, gives rise to entities that those original particles could never have been alone. The magnon carries no charge and only spin, and it may one day carry information without the heat that haunts electric computation. The plasmon carries the sloshing of the whole electron ocean, and it coloured the glass of a Roman drinking cup with physics that would not be named for 1600 years. The polariton is half matter and half light, and neither and both, forming condensates at temperatures where condensates seemed impossible. The Cooper pair is 2 reluctant electrons made into partners by the matchmaking lattice, condensing into a frictionless river that flows forever. And in all of them, in every one, you can hear the same note sounding. The particle is not inside the atom. The particle is in the relationship between atoms. In the agreement and the disturbance of the agreement, in the coordination and the interruption of the coordination, in the whole and the particular way the whole can move. That is the note this narration has been building toward, and it has not yet been stated in its fullest form. The magnon, the plasmon, the polariton, the Cooper pair, these are not the end of the inventory. There are still places further in, where the emergence idea reaches its most extraordinary and most recently confirmed expression, where the quasiparticles that arise are stranger than anything we have yet named, existing only in 2 dimensions, carrying fractions of the electron's charge. remembering things that particles in 3 dimensions are not permitted to remember. But that is the next turning of the road. For now, let the Cooper pair be the resting place. 2 electrons, enemies by nature, made into partners by a crystal's patience. Flowing together, forever, at temperatures cold enough and in materials compliant enough to let them be what the math permits them to be. The lattice is cold and still, the pairs are forming, the current flows, and there is nothing in the world of ordinary physics large enough to slow it down. There is a moment in the history of a cooling experiment when the temperature crosses a line and something in the world changes its nature so completely that the very act of watching it feels like watching a law being broken. That moment has a name. It is called the lambda point. Liquid helium-4, cooled in a laboratory to approximately 2.17 degrees above absolute zero, passes through this point the way a door swings open. Above it, helium is a cold liquid like any other, heavy and sluggish and perfectly ordinary in its behavior. It sloshes, it resists, it moves the way a fluid is supposed to move, with friction, with viscosity, with the ordinary internal drag of molecules brushing past each other. Below it, something entirely different is there, wearing the same name. The liquid has not frozen. It has become something for which, when Piotr Kapitsa first reported it in 1938, and John Allen confirmed it almost simultaneously, the only available word was superfluid. Kapitsa's Nobel Prize, awarded in 1978, would eventually acknowledge a career's worth of contributions, but the superfluid discovery is what fixed his name in the story being told here. He watched the helium below 2.17 Kelvin do things that should not have been possible. The viscosity of the liquid, the internal friction that slows all ordinary fluids, dropped effectively to zero. Not reduced. Not lowered to a very small number, zero, or close enough to zero that every experiment designed to measure it found nothing there to measure. A fluid with no resistance to its own flow. And then, it did something even stranger. It climbed. Place a container of superfluid helium-4 inside a larger vessel, and the liquid will creep up the inside walls of the container, over the rim, and down the outside, an invisible film of helium climbing upward against gravity, driven by the same zero viscosity that lets it slide into and through any opening the liquid finds. It leaks through pores that stop ordinary liquids. It flows through cracks too fine to see. It will, if given enough time and surface to work with, empty itself from any container that is not specifically designed to confine it. There is no magic in it. But there is something that looks like magic until the physics names what is happening underneath. Lev Landau, whose name has moved through this narration like a recurring figure in a dream, the theorist of the Fermi liquid, the proposer of the polaron, the architect of so much that is careful and deep in condensed matter physics, turned his attention to superfluid helium in 1941, 3 years after Kapitsa's discovery. Landau's theory was, like everything else his name is attached to, a theory not of individual atoms, but of collective excitations. He did not ask what a single helium-4 atom was doing below the lambda point. He asked what patterns of collective motion the liquid permitted, and what those patterns' properties would be. His answer was the same answer this narration keeps returning to. The physics of the superfluid is the physics of its quasiparticles. Below the lambda point, Landau said, the low-energy excitations of the liquid come in 2 kinds. One kind you already know, phonons, the quantized sound waves, the ripples of compression and expansion moving through the liquid the same way they move through a crystal lattice, carrying energy in discrete packets, behaving as particles the way a single atom cannot. Phonons appear in the superfluid as they appear everywhere that atoms are arranged and vibrating, because the vibration of many is always, at the quantum scale, a set of countable, particle-like lumps of energy. But the second kind Landau introduced was something genuinely new. He called them rotons. Think, if you want a picture, of a tiny localized vortex, a microscopic whirlpool, quantized, carrying a specific energy and momentum that the phonon branch of excitations could not account for. The phonon describes the long, low, lazy waves of sound moving through the liquid. The roton describes something more like a compact, spinning disturbance, a minimum of energy sitting at a specific momentum value on the excitation spectrum, a dip in the energy landscape that Landau could trace mathematically and whose consequences matched what the experiments measured. This is the elegance that should settle around you as you listen. Landau could not directly photograph a roton. No one can isolate one and hold it up to the light. What Landau could do, and did, was show that if you treated the superfluid's excitations as a gas of phonons and rotons, each with defined energies and momenta and the ability to scatter off each other, the predicted properties of the liquid matched the measured ones: the zero viscosity, the specific heat, the speed of sound in the liquid, the way heat flows through it. All of it came out of the quasiparticle description, which meant the quasiparticle description was capturing something true about the system, even if the roton and the phonon were not objects you could pick out of the liquid with tweezers. Emergence, again, the whole liquid, its atoms in quantum mechanical coordination, hosting patterns of motion that obey particle rules, and those patterns being the only vocabulary the physics needs. Landau received the Nobel Prize in Physics in 1962. The prize recognized his theories of condensed matter, and the superfluid work was central to that recognition. It is worth noting the timeline. The theory came in 1941, the prize in 1962, and in the intervening 2 decades the quasi-particle framework that underlay his superfluid description had proven itself indispensable across material after material, phenomenon after phenomenon. The prize was not for a single discovery, but for a way of thinking, a way that said, "Whenever many particles are bound together, ask not what the individual particles are doing, but what collective excitations the system can support." That question is always the right one. Let the superfluid rest now. Let it pool at the bottom of its container, invisible film climbing the glass in the cold, and carry with you just one thing. Even a liquid that defies every ordinary rule of fluid behavior is, underneath, a story about quasiparticles, about phonons and rotons moving through coordinated helium, and the collective choreography producing something that looks, from outside, like a miracle. Now, the open loop this narration planted in an earlier turning of the story, the one that may have felt almost too strange to hold, it is time to close it. The electron cannot be divided. This is not a hypothesis. It is one of the most thoroughly tested facts in all of physics. Take an electron and try to cut it. Apply any force you have available. Subject it to any experimental procedure your ingenuity can devise. The charge that comes out will be the electron's charge, or zero. You cannot peel off a fraction. The electron is, in this sense, elementary, a thing that has no smaller version of itself nested inside. And yet, In 1982, Daniel Suey and Horst Stramer were experimenting with a two-dimensional sheet of electrons, a thin layer of semiconductor sandwiched between insulators, cooled to millikelvin temperatures, placed in a powerful magnetic field. The experiment was a refinement of the quantum Hall effect already discovered, in which the conductance of such a sheet, measured perpendicular to the current, came in exact integer multiples of a fundamental constant. Clean, beautiful, perfectly understood. What Suey and Stramer found was not that. Their device, cleaner than previous ones, colder, in a stronger field, showed conductance plateaus at fractional values. 1/3, 1/5, 2/3, other fractions with odd denominators, fractions of the fundamental unit. The integer quantum Hall effect was a settled matter. The fractional quantum Hall effect was, in Stramer's own description, a bolt from the blue. There was no single particle to account for it. No one had modified the electron. The electrons in the device were the same indivisible electrons they had always been. But the collective quantum state those electrons settled into at these extreme conditions, the particular way two-dimensional electrons in a strong magnetic field arrange their mutual interactions into a correlated whole, allowed that whole to support excitations with fractional charge. The quasiparticles of the fractional quantum Hall state carry exactly 1/3 of the electron's charge if the filling fraction is 1/3. Not approximately 1/3, not 1/3 as a rough label, exactly 1/3 as precisely as any measurement has ever confirmed. Robert Laughlin worked out the theory in 1983. His wave function, the mathematical description of the correlated electron state, predicted the fractional charge and explained why these quasiparticles could exist. The whole electron sea, locked into a specific correlated pattern by the cold and the field, behaves as if it contains objects carrying E divided by 3. The objects are real, they scatter off each other, they have measurable properties, they register in experiments. The shot noise experiments came in 1997. Two independent groups, one in Saclay, one at the Weizmann Institute, designed experiments sensitive enough to detect the granularity of the current, the fact that current is carried in discrete lumps, and that the size of the lump tells you the charge of the carrier. If the carriers were electrons, the shot noise would have one characteristic magnitude. If the carriers were quasiparticles with 1/3 the electron's charge, the shot noise would be 3 times smaller. It was 3 times smaller. Exactly, the fractional charge was not theoretical anymore. It was measured in a detector, in a laboratory reproducibly. Suey, Stramer, and Laughlin shared the Nobel Prize in Physics in 1998. Sit with that for a moment, in the quiet. The electron is indivisible. The electron C, in the right correlated state, carries excitations with 1/3 of the electron's charge. Both of these things are true. There is no contradiction in the second fact, because the quasiparticles of the fractional quantum Hall state are not fractional electrons, they are not pieces broken off of electrons. They are patterns of collective behavior that the whole system of electrons can support, and those patterns carry fractional charge because that is what the mathematics of this particular collective state permits them to carry. They are as real as anything in the measurement, and they are made entirely of electrons, the way a whirlpool is made entirely of water without there being a whirlpool inside any water molecule. Emergence in its most extreme expression. The parts are one thing, the pattern the parts can form is something else entirely, and the something else is real. Now the story reaches what might be its most extraordinary waypoint. The fractional quantum Hall quasiparticles have a property that goes even further than fractional charge. It concerns what happens when you swap two of them. In three-dimensional space, there are exactly two kinds of particles, sorted by what happens to the quantum state of the system when you exchange two identical ones. Bosons, photons, Cooper pairs, helium-4 atoms have a quantum state that is unchanged by the exchange. Swap two bosons and the mathematics comes out the same. Fermions, electrons, protons, neutrons have a quantum state that picks up a minus sign when you exchange two. The number -1. These are the only options three-dimensional quantum mechanics permits. Bosons or fermions, +1 or -1. The quasiparticles of the fractional quantum Hall effect existing in a two-dimensional system are not obligated to follow this rule. In two dimensions, the mathematics opens up. When you exchange two of these quasiparticles, or more precisely, when you take one and drag it around the other along a closed path, returning it to its original position, the quantum state of the system picks up a phase factor that is not +1 and not -1. It can be any value on the unit circle, any angle, any rotation in the complex plane. This is what Frank Wilczek named in 1982, the same year Sui and Strama made their discovery. Wilczek, recognizing that these two-dimensional quasiparticles could have exchange statistics unconstrained by the boson-fermion binary, called them anyons. The name is precise in its looseness, enyon, a particle that can pick up any phase when exchanged. The electron must pick up -1. The photon must pick up +1. The enyon can pick up any number in between or beyond, depending on what collective state it is an excitation of. This is not a mathematical abstraction that exists only in equations. The enyon exists in the sense that the quasiparticles of the fractional quantum Hall state are enyons, and those quasiparticles have been measured, their fractional charge confirmed. Their enyonic character the subject of a decade of experimental effort. In 2020, that effort bore fruit. Two separate experimental groups, one at the Paris Centre National de la Recherche Scientifique, working with a refined quantum Hall interferometer, and one at Purdue University, working with a particle collision approach, published results that provided direct experimental evidence of enyonic braiding statistics. The braiding, the term deserves a moment's attention. When you take one enyon and loop it around another, returning it to where it started, the technical name for the operation is a braid. You have woven the path of one particle around another, and the weaving has changed something about the quantum state of the system in a way that depends not on where the particles are at the end, but on the history of how they moved. The topology of the path, the number of times one looped around the other, determines the effect. The geometry of the endpoints does not. This is why the word braid is used, and not the word exchange. Exchange suggests you pick one particle up, put it where the other was, and put the other where the first was. Braiding goes further. It is a process, a choreography, a sequence of moves in space that the system remembers. And the system's memory of that choreography is encoded in its quantum state. The enyons confirmed in the 2020 experiments are what physicists call abelian enyons, named for the mathematician Niels Henrik Abel, because the order in which you perform their braidings does not matter. Braid A around B, then B around A, or reverse the order, the result is the same. The phase is the same. The memory is commutative. There is another class, non-abelian enyons. These are quasiparticles for which the order of braiding operations matters. Do them in one sequence, and the quantum state ends up one way. Reverse the sequence, and it ends up differently. The system's memory is non-commutative. This is a radical property for matter to have. It means the quantum state of a system hosting non-abelian anyons contains information. It has been changed, in a specific and calculable way, by the history of how the anyons were moved around each other, and that information is stored not in any single particle's local state, but in the shared topology of all the paths. A Majorana zero mode is the most studied candidate for a non-abelian enyon. The name honors Ettore Majorana, the physicist who in 1937 described a particle that is its own antiparticle. A Majorana zero mode is not quite that, but it is a quasiparticle excitation at the boundary of a topological superconductor, a special material that superconducts and also has topological properties that protect certain boundary states from being perturbed. The Majorana zero mode sits at the edge of such a material, at zero energy, and its anyonic braiding statistics are non-abelian. Alexei Kitaev proposed in 2003 that non-abelian anyons could form the basis of a quantum computer that is, by its nature, protected against the errors that plague ordinary quantum computers. This is the idea of topological quantum computing, which has been central to Microsoft's quantum research program. The protection comes from the same property that makes non-abelian anyons strange. The information is stored in the braiding history, in the topology of the paths, and local noise, a stray vibration, a fluctuating magnetic field, a cosmic ray passing through, cannot accidentally change a topology. You cannot untie a knot by bumping the string. The information encoded in the braiding is robust in a way that information encoded in the local state of a fragile qubit is not. Whether Majorana zero modes will deliver on this promise is an open question as of the time this narration is being written. The experimental hunt for them has been long and sometimes controversial, but the theoretical framework is sound, and the anyons it rests on, the abelian ones, have now been directly observed. The story is not finished, but its outline is clear enough to follow, and what it outlines is extraordinary. A form of computing whose foundation is the woven history of quasiparticles, particles that exist only in two dimensions and are themselves made of the correlated behavior of electrons that cannot be divided, but can, collectively, do things that no single electron is permitted to do. From the phonon, the simplest collective motion of atoms in a lattice, the vibration that propagates like a wave and arrives like a particle, to the enyon, the two-dimensional quasiparticle that remembers being braided. That is the range of the emergence idea. And the same logic runs through all of it, without a gap. There is one more thing the quasiparticle framework gives us to consider before the narration can settle into its close. It is the thing that, in some ways, most clearly separates a quasiparticle from a fundamental particle. The thing that most honestly earns the prefix quasi. And it is also the thing that most gracefully resolves the tension the word illusion was always going to raise. A quasiparticle has a lifetime. A true elementary particle, an electron, a proton, a photon propagating through vacuum, does not decay by virtue of being what it is. It persists. The electron in a hydrogen atom, undisturbed, will remain an electron indefinitely. Nothing internal to the particle is counting down. It is not made of anything more fundamental that can come apart. A quasiparticle is different. The phonon propagating through a crystal will eventually scatter off another phonon, off an impurity, off a grain boundary in the material, and when it does, The energy it carried redistributes, the collective mode dissolves, and the phonon is gone. Not transformed into something else, the way a photon can be absorbed. Dissolved back into the sea of atomic vibrations from which it briefly distinguished itself as a coherent pattern. The quasiparticle exists only as long as the pattern holds, and the pattern holds only as long as the coherent excitation is not destroyed by the environment it moves through. This lifetime is not an accident or a defect. It is a defining characteristic, and it is precisely predicted by the theoretical framework. The Fermi liquid theory that Landau built in the 1950s, the theory that describes the dense, interacting electron gas in a metal as a collection of weakly interacting quasi-electrons, predicts not just that quasi-electrons exist, but how long they live. Near the Fermi surface, the energy surface that separates occupied from unoccupied electron states, the quasiparticle lifetime grows. The closer a quasi-electron's energy is to the Fermi surface, the longer it persists before scattering, and in the limit, right at the Fermi surface itself, the lifetime diverges, meaning the quasiparticle is arbitrarily sharp and long-lived. This is what makes the Fermi liquid description self-consistent. The quasi-electrons near the Fermi surface are well defined enough to be treated as particles, because they live long enough to carry momentum, to scatter, to be tracked by the formalism. Away from the Fermi surface, the lifetime shortens. The quasiparticle becomes blurrier, less well-defined, more quickly lost to the background. This lifetime, this sharpness or blurriness of the quasiparticle's existence, is directly measured by a technique called angle-resolved photoemission spectroscopy, which goes by the acronym ARPAS. The technique works by shining light on a material's surface and measuring the energy and momentum of the electrons that are kicked out. If those electrons were occupying a well-defined quasiparticle state inside the material, they emerge with a specific energy and momentum, and the ARPAS spectrum shows a sharp peak. A peak that is the signature of a coherent, particle-like excitation inside the solid. If the quasiparticle is short-lived or poorly defined, the peak is broad and smeared. The sharpness of the particle replaced by a haze of possibilities. ARPAS reads the quasiparticle lifetime in the width of the spectral peak, and by doing so confirms, experiment by experiment, that the lifetime predicted by theory is the lifetime that nature delivers. There is something worth pausing on here, in the quiet of this late passage of the narration. The quasiparticle has a lifetime. It is born, meaning a collective pattern coalesces out of many particles acting together, and it dies, meaning that pattern dissolves back into the undifferentiated behavior of the whole. Between birth and death, it carries momentum, charge, spin, energy. Between birth and death it scatters, decays, propagates, interacts with other quasiparticles, just as elementary particles interact with each other. The entire arc of a physical particle, emergence, existence, dissolution, is compressed into something that may last for a few femtoseconds or a few microseconds, depending on the material and the quasiparticle type. Mortality as a defining trait. It is not a limitation to be apologized for. It is the most honest statement of what a quasiparticle is, a pattern that the collective allows, for as long as the collective allows it. And now the narration arrives at the place where the philosophical spine has been waiting. In 1972, the Nobel laureate Philip Warren Anderson, physicist at Bell Laboratories and later Princeton, one of the central figures in 20th century condensed matter physics, published an essay in the journal Science. It was not a research paper, it was 4 pages of argument, densely written, carrying the title, "More is Different." The argument was this: science has a reductionist tradition. To explain something at one level, you look for the principles operating at the level below. To explain chemistry, you look to atomic physics. To explain atomic physics, you look to particle physics. The implicit assumption in this tradition is that if you understand the laws at the most fundamental level, you can, in principle, derive everything above. The whole is, in the end, just the sum of the parts, and knowing the parts completely would be knowing everything. Anderson disagreed. He argued that at each new level of complexity, at each new scale of organization, entirely new properties emerge that are not predictable by simple extrapolation from the level below, and that cannot be reduced to it without missing something essential. The laws of the new level are their own laws. They take the building blocks from below and do something with them that the building blocks themselves do not contain. Superconductivity is not a property of a single electron. Superfluidity is not a property of a helium atom. Magnetism is not a property of a proton. Each of these is a property of a collective, and the collective owns it in a way that the individual parts do not. The essay's title is its thesis, "More is Different." Not just more in quantity, more in kind. A sufficiently large and complex collection of things can do things, be things, that no individual thing in the collection can do or be. Quasiparticles are the mathematical formalization of this principle. They are the language the physics uses to state, precisely and computably, what the collective can do that the parts cannot. When many electrons coordinate into a fractional quantum Hall state, the state is permitted to have excitations with fractional charge, not because any electron has fractional charge, but because the collective does. When many atoms vibrate together in a crystal, the vibration is permitted to exist as discrete, particle-like quanta, not because any atom is a phonon, but because the relationship between atoms is. When 2 electrons are paired by the lattice into a Cooper pair, the pair is permitted to condense and flow without resistance. Not because any single electron is frictionless, but because the pair is a new kind of entity with properties the individual electrons do not possess. More is different, and the difference is the quasiparticle. Anderson's essay was 4 pages. Its influence has been, in the decades since 1972, enormous and ongoing, not just in condensed matter physics, but in biology, in neuroscience, in economics, in any field that must think about how complex systems produce properties their components do not carry. The essay showed up in physics, but what it was saying was something broader. The universe is not exhausted by its elementary constituents. The constituents are real. The patterns they form are also real. The patterns are not more real than the parts, but they are not less real either, and they require their own descriptions, their own laws, their own vocabularies. Which brings the narration to its last task. The word that was always lurking in the wings of this story, waiting to be addressed honestly. The word illusion. It is tempting to describe quasiparticles as illusions, and the temptation has a certain poetic appeal. A phonon is not there in any single atom. Look inside one atom and you find nothing phonon-like. A magnon is not the spin of any one electron. Isolate an electron and you have no magnon. They are, in this sense, the physics of what is not there in the individual piece. They are properties of the relationship, the pattern, the whole. And it is natural, reaching for language to say that something whose reality lives in the relationship rather than in the individual object has a quality of the fictional, the projected, the not quite there. But the word illusion carries a second implication, and it is this implication that must be turned back. An illusion is something that does not do what a real thing would do. A mirage of water in the desert does not wet your tongue. A reflection of a candle gives no heat. If quasiparticles were illusions in this sense, constructs that do not interact, that leave no trace, that register in no detector, then the word would be apt, and the dismissal would be deserved. They are not illusions in this sense. They are not in that category. A phonon carries heat through a crystal. Measure the thermal conductivity of diamond, and what you are measuring is the behavior of phonons. A polaron moves through a material, and its heavier effective mass slows it down in ways experiments confirm. An exciton in a solar cell absorbs a photon and migrates toward the junction where it releases its energy as current. That current is real, the device runs on it, the light becomes electricity, and the electricity does work. The Cooper pairs in a superconductor carry current with zero resistance, and the zero resistance is demonstrable. Set up a current in a superconducting ring, and it will still be flowing unchanged, months later, years later, without any energy input. The fractional charge of the quantum Hall quasiparticles was measured in the shot noise experiments of 1997 with the same rigor as any other measurement in physics. The anyons were braided in the 2020 experiments, and their braiding statistics confirmed. These things interact with other things. They carry momentum that can be transferred. They scatter in ways that determine the electrical resistance of every metal wire you have ever used. They are what every transistor relies on, the electron hole, the quasiparticle, that is a positive charge made of an absence, runs through the semiconductors that run the devices that run everything. The quasiparticle is not somewhere beyond the reach of the world. The quasiparticle is what the world is running on. What is true is that they are not fundamental. They are not elementary building blocks hiding inside the atom, waiting to be found at smaller and smaller scales. They are emergent, properties of the collective state of matter, arising when many things organize in particular ways, existing as long as the organization holds, dissolving when the organization breaks down. Their reality is a different kind of reality than the reality of an electron in vacuum, but it is not a lesser kind. The phonon and the electron are both doing real physics. The phonon is doing it collectively. This is the honest resolution of the illusion tension, and it is a resolution that opens rather than closes. Because if the quasiparticle is real in this sense, if emergence produces genuine, measurable, interacting entities that the parts did not contain, then the universe is richer than any inventory of its elementary components would suggest. There are not just electrons and quarks and photons, there are also all the patterns that assemblies of electrons and quarks can form, and those patterns are real in the same way their components are real. And they carry properties their components do not carry, and they obey laws their components do not directly obey. The universe contains not just its ingredients, but everything its ingredients can collectively become. That is a larger universe, not larger in size, larger in the depth of what can be there, in the richness of what matter can be. A crystal, in this light, is not just a regular arrangement of atoms. It is a medium in which phonons live, in which vibrations become particles, in which sound is granular, in which heat is a gas of discrete things propagating and scattering. A semiconductor is not just a material with a gap in its electronic structure. It is a medium in which excitons and holes move, in which an absence carries charge and energy moves as bound pairs of electron and void. A magnet is not just a collection of aligned spins, it is a medium in which magnons propagate, in which magnetism ripples like waves on water, and those waves can carry information at the cost of almost no heat. A superconductor is not just a material that conducts perfectly. It is a medium in which Cooper pairs condense into a single coherent quantum state that flows without the smallest resistance, a river that once set in motion loses nothing. And a two-dimensional electron gas in a strong magnetic field at millikelvin temperatures is not just an extreme version of an ordinary conductor. It is the medium in which fractional quasiparticles emerge, in which charge can come in thirds of an electron, in which anyons braid through each other and remember the history of their paths, in which the topological encoding of information becomes not a theoretical possibility, but a measured reality. The same idea, one idea, running through all of them, from the simplest vibration of a salt crystal to the braided paths of anyons in a quantum Hall device, from the sound of a phonon propagating through diamond to the frictionless river of Cooper pairs in a cooled metal, from the roton spinning in superfluid helium to the polariton that is half light and half matter existing in a resonant cavity. The same note, differently instrumented. Emergence, the collective, can be more than the sum of its parts. Not metaphorically. Literally, mathematically, measurably, the whole hosts entities the parts do not contain, and those entities are real. This is the thing the quasiparticle is trying to tell you if you give it the quiet to speak. The world you walk through every day, the metal of a doorknob, the semiconductor in a phone, the glass in a window, the magnet on a cabinet, is full of these collective entities. They are moving through matter right now as you listen. Phonons are carrying heat away from your skin into the cool air. Electrons in the circuits of whatever device is speaking this narration to you are moving through a sea of impurities and lattice vibrations, their progress governed entirely by how well-defined their quasiparticle states are, how long-lived, how sharp. The light reaching your eyes, if you have them open, is coupling to excitons in your retinal molecules. Its energy moving through your biology in forms that look nothing like a photon, but carry the photon's legacy into the mechanism of sight. The solid world is not made of solitude, it is made of agreement. And out of the agreement arise the patterns, the phonons, the holes, the polarons, the excitons, the magnons, the plasmons, the polaritons, the Cooper pairs, the rotons, the anyons, each one a specific kind of pattern, each one obeying rules that the individual parts do not obey. Each one real in every way that the word real is allowed to carry. You were told, somewhere in the course of your education, that matter is made of particles. And it is. But the particles inside a solid are, for the most part, not the elementary particles of empty space. They are something that only exists because the matter is full, because the atoms are together, because the electrons are many, because the whole has coordinated into a collective state that licenses these new entities to exist within it. You cannot find a phonon in a single atom. You cannot find an exciton in isolation. You cannot find a Cooper pair without the lattice's patient mediation. They require the collective. They are born of it and dissolve back into it. And perhaps there is something in that worth carrying into sleep. The most interesting things are not always the most solitary. The most remarkable properties are not always the properties of the smallest things. Sometimes the richness is in the relationship, in the coordination, in the pattern that arises when enough things are together and the conditions are right. Sometimes the particle you are looking for is not hiding inside anything. It is the behavior of everything, and that behavior is real, and it has a name, and the name is earned. Phonon, exciton, hole, polaron, magnon, plasmon, polariton, Cooper pair. Roton, anion, each one a collective motion with a particle's passport. Each one Lev Landau's insight made specific, Philip Anderson's principle made vivid, Igor Tam's naming made linguistic, Felix Bloch's calculation made magnetic, Bardeen, Cooper and Schrieffer's theory made frictionless, Piotr Kapitza's cold helium made fluid, Daniel Suey and Horst Stramer's device made fractional, Frank Wilczek's topology made anionic. Each one the same story told in a different material, at a different temperature, in a different regime of energy and charge and spin. The same story. One story. And you have heard it now, in its fullness, from the phonon at the beginning to the enion at the end. From the simplest vibration to the most exotic braiding. From a crystal at room temperature to a two-dimensional electron gas at millikelvin cold, held in a magnetic field strong enough to change what particles are permitted to exist. You have heard the whole arc. And the arc ends not in confusion, but in a particular kind of clarification that is also, in its own way, a deepening. The quasi-particle is not an illusion. It is an emergence. It is real, and it is collective. And it is the answer to the question of what the particle actually is when the particle is inside a solid. Not a smaller thing hiding there. A pattern of many things, coordinated, behaving together in a way that earns the name. The lattice of the crystal is quiet now, in the imagination of this narration. The phonons are moving through it, carrying the last of the warmth from where the day was to where the night is. The spins in the magnet are tilting gently, sending magnon ripples across the ordered sea. The electrons in their bands are heavy with the lattice's embrace, polarons moving slowly, feeling the weight of everything they carry. The superfluid helium is climbing its glass wall in the cold, unhurried and silent. The fractional quasiparticles in their two-dimensional plane are drifting with their fractional charges, remembering every path they have woven through each other. And somewhere in a laboratory, someone is measuring the lifetime of a quasiparticle with ARPs, watching the spectral peak narrow as the temperature falls, watching the collective excitation become sharper, more particle-like, more fully itself. Watching the quasiparticle live its brief and entirely real life before dissolving back into the sea that made it. The narration has kept its promise. The quasiparticle is real. The emergence is the mechanism. The collective motion is the particle. And the solid world, the ordinary material world you touch and sit in and move through, is full of entities that only exist because the atoms are together, because the electrons are many, because the whole is always, quietly, more than it appears. That is the curiosity this journey was carrying, and it is settled now, gently, for the night. Sleep well, fellow voyager. The next journey keeps until you wake.